We've been at the forefront of automotive engineering innovation from the beginning, from the Model T to the fully autonomous vehicles of today. With the next automotive revolution happening right before our eyes, SAE's quantifiable research and reliable technical documentation are more crucial than ever. Connected vehicles, electrified vehicle technology, and sustainable transportation are just a handful of the areas where SAE International supports those who shape the future for the mobility of tomorrow. With more than a century of experience, a powerful and growing cohort of shared knowledge, backed by a global community of more than 200,000 engineers, technical experts, and volunteers, SAE continues to curate the most reliable and comprehensive collection of engineering resources and consensus-based mobility standards on Earth. Movement defines life. SAE lives to define movement.
Welcome everyone to Using Artificial Intelligence to Understand Vulnerable Road Users virtual technical meeting. Thank you for joining us today, and a big thanks to the SAE Detroit section for hosting this event. I'm Peter Groth, your moderator and one of the presenters. So just a little background about me. I'm the Research and Innovation Manager working in comfort and driving assistance systems here at Valeo North America. I also run our San Mateo, California office. I've been with the company for 25 years, working on product development, program management, and now in research and innovation. So before we start, I want to address a couple housekeeping items. All participants are automatically muted with their cameras off. We do encourage you to ask questions, but to do so with the chat function. At the end of the meeting, we'll take the last 15 minutes to address these questions. This presentation is being recorded and will be posted on the SAE Detroit section YouTube channel at a later date. Today's presentation has two parts, plus some time for Q&A, as I mentioned. So I'll start with a short overview of the company and then hand over to Jagdish Bhanushali, who is our senior software engineer and expert in machine learning, who will take us through his work on today's topic. So with that, we're proud to announce that Valeo has turned 100 years old this year. We're celebrating a century of innovation. Our motto is to build a cleaner, safer, and smarter mobility. So in those 100 years, a lot has changed, particularly in the type of products we build. In the beginning, we started with friction materials for brake linings and clutches, and today most of our products contain electronics. Our strategy is based on four things that are happening today in the automotive industry. The first is, of course, the acceleration of electrification. So this is the rise of EVs, where a lot of our products are now geared to servicing that trend. There's also the rise of ADAS, the acceleration of ADAS, where for anyone who's recently bought a car has probably noticed there's a lot more systems helping you as you're driving. These are becoming standards, in some cases mandated. There's also the lighting, which has been changing in the vehicle. It's more than just headlamps and tail lamps. It's really about the design language of the vehicle. So it's taken on a new meaning, we would say. And then there's the interior experience. And this is where the cockpit of the vehicle, the inside of the vehicle is also changing with more sensors and, let's say, different displays and different ways of interacting with the vehicle and interacting with you. So our company is divided into four business groups and the Valeo service aftermarket activity. Jagdish and I represent comfort and driving assistance systems. This is the part of the business that deals with perception sensors, ADAS systems, interior monitoring, heads-up displays, control surfaces, and also telematics units. On the visibility side, we do everything about seeing and being seen. So this can be headlamps, tail lamps, so exterior lighting, but also interior lighting, and wipers, and sensor cleaning, which is also, I would say, a new importance in the coming world where sensors also have to be kept clean. Powertrain is all about electrification. So this can be 48 volt technology for hybrid, but also high voltage, where we do e-motors, DC-DC converters, onboard chargers, and also a charging station. And on the thermal side, everything about heating and cooling the vehicle, which has also changed quite a bit now that we're dealing with EVs more, where we don't have a lot of that excess energy we used to have in the ICE motor. The company itself has, in 2022, did 20 billion in sales in euros. We have 110 people worldwide, and we're very global. We're present in 29 countries. We also like to be very close to our customers in where they produce and develop their products. So that explains why we have 183 production sites and 65 R&D centers. Our commitment to protecting the environment is reflected in our innovations, which create new eco-responsible products. And it can also be seen in our environmentally efficient industrial processes, where we work with our suppliers toward achieving our sustainability goals. So we made a very strong and ambitious commitment to achieve carbon neutrality by 2050, and we will reach 45% reduction by 2030 compared to 2019 across our entire value chain, including CO2 emissions from our suppliers, our own operating activities, and importantly, the end use of our products. So sustainability is at the center of our strategy, and we also contribute to the circular economy, which is a system to eliminate waste and to promote efficient and better use of resources. So this is basically to stop waste from being produced in the first place. And to deal with this within our company, we've rolled out what are known as the 4Rs. So this starts with the design of products, that they are optimized for the use phase in their design, in the fact that in the future products need to also be remanufacturable. So we have a lot of experience with this with certain product lines, and we hope to double this by 2030. Also, part of this is, of course, to make products repairable, serviceable, instead of throwing them away when they go bad. And for this, also with the increasing content of electronics, we see opportunities to introduce repair into our operations. And finally, it's also about recycling. So a lot of the products these days will use recycled materials, but also our operations will rely on circularity. So recycling there also waste and water. So all of this has led to a successful transformation we've had. We're a leader in both electrification through our powertrain and thermal business groups, but also ADAS through our comfort and driving assistance business. And we're proud to say that today 1 in 3 cars equipped worldwide have our thermal and electric systems and also our ADAS solutions on board. So coming closer to the subject at hand today, we're also a leader in ADAS with full stack capability, combining our sensors, control units, and software. So we have a strong history in the different sensing technologies. We have a full portfolio, which includes things like ultrasonic sensors, cameras, radars, and LiDAR. We're particularly proud of LiDAR being the first to market with automotive-grade LiDAR solutions. We're now in our 3rd generation of LiDAR. And all of this combined, of course, onto control units that start with the parking systems that combine surround view with ultrasonics, all the way up through high-power compute solutions and zone controllers. We also offer the software solutions that go onto that to do the different functionalities and also the integration of the complete system. So these days, we're seeing a change to the software design vehicle in the industry. So we're going from this distributed architecture where all the functions were contained on their own units added to this car, to a more centralized architecture through domains, and finally going to zonal and high-power central computes. And this is also changing the type of software that we're going to be able to put onto vehicles in the future. It also means that the sensors are changing. They used to be very smart components with onboard functionality. Now they become more satellite components with very high-quality data coming out of them. And this flows, of course, into central controllers, through zonal controllers, also products which we are offering. But finally, it also means that software changes. It's no longer tied to the hardware. It's now also a product, and it can reside in various places in the architecture. So we offer the full software stack, including the core software, the tool chains, data management, and system validation. And we have, of course, a strong history in various applications around active safety, parking, maneuvering, and driving automation. These can, of course, be inserted at various points in the stack. So, coming to the subject today, we've been a leader in the use of artificial intelligence in automotive applications, and we use it to expand the functionality of modern vehicles. So the core of this is to use AI to understand, predict, and decide. So the one side, it's about understanding what's around a car. This is about classifying what's happening in the environment, different pedestrians, vehicles. Also segmentation, figuring out what the road is and what's on the road in terms of markings, etc. Then using all of this information to predict what could happen next in the next time horizon. And then based on those predictions, to decide what is the safest course of action, most efficient course of action that a vehicle needs to take. So our interest is to make cars understand the world much in the way we do, able to pick up cues in the environment in the same levels that humans can. And this is not yet where we're at today completely, it's where we want to go, and that's some of the work that we're going to show you today. So I'm very proud to hand over the rest of the presentation to Jagdish, who has worked in our MovePredict.AI and Pantomime solutions here at our tech center in California.
Hello everyone, I'm Jagdish Bhanushali, Senior Software Engineer at Valeo. I joined Valeo 6 years ago as an intern and moved my career up as a Senior Software Engineer. I'll be now talking about MovePredict.AI and Pantomime for next 45 minutes or so. One of key challenge for automated driving is that vehicle have to constantly interact with pedestrians, cyclists, etc., generally identified as vulnerable road users. Human drivers are very good at understanding the state of pedestrians and predicting the intention of road users. But to achieve naturalistic driving behavior in safely navigating the scene, automated vehicle need to understand this level of human intelligence. So that's why we have implemented MovePredict.AI. MovePredict detects pedestrians in the scene and identifies if pedestrian is going to cross the street or not. It uses Valeo's fisheye camera and LiDAR system to navigate safely in the urban environment. Most of research in autonomous driving focus on object detection and using this detected object in the scene for path planning. But very less research has been done on pedestrian intention and understanding their behaviors. Our research is mainly focused on finding low-level perception module, which detects pedestrian in the scene, understand behavior of pedestrian, and find out intention of crossing. Our objective also includes understanding the vehicle surrounding and trajectory of all the vulnerable road users to understand them better. Autonomous vehicles have a feedback loop which flows from sensor to controls, where perception module uses data collected from sensors, gather useful information, and pass it to control module so that control can be applied accordingly. Vital components to work harmoniously within autonomous vehicle are object detection, scene understanding, localization, and path planning. Together, they form the backbone of the groundbreaking technology. Scene understanding need to know all static and dynamic actors of the scene, and MovePredict focus very well on this static and dynamic actors. By fusing data from LiDAR, we accurately identify pedestrians, their distance from the car, their world coordinate, and their past trajectory, which can help us to avoid the collision. As a driver, we understand the body language of all road users, and based on that, we correct our driving behavior. Similarly, if we want to give same intelligence to the car, it need to understand body language of pedestrians. One way to do so is by understanding the pose of pedestrians and tracking their pose throughout the time to predict their actions. If we track the bone joints of pedestrians, that gives vital information of their behavior. And that is the reason why we wanted to train our model on human pose estimation. For our pose estimation training, we have used COCO key point dataset and pose track dataset. Tracking the pose can tell if person is walking or standing or doing some other activities. But having only pose information is of the pedestrian is not enough. It gives only local context. To understand global context, we also need to know where in the scene this pedestrian is present and what does overall global scene look like. For this purpose, we have also used semantic scene segmentation, where we use cityscape dataset uh, to understand pixel level annotation and have the classes which we see on the road. Now, since we have the perception backbone using which we understand the environment, now it's time to find right data set for the task which we are aiming for, that is the pedestrian crossing intention. One of the main challenge for deep learning based intent prediction for AD is creating this behavioral annotation for VRUs from natural driving behavior. This problem is mostly addressed by JAAD dataset by providing rich behavioral label for pedestrians. The JAAD, which stands for Joint Attention in Autonomous Driving dataset, is a dataset for studying joint attention in the context of autonomous driving. The dataset aimed to provide data for pedestrians, detect pedestrian deductions, pedestrian actions, and gesture recognition, and behavioral studies of traffic participants. In this dataset, focus is on pedestrians and drivers' behavior, where dataset is not only annotated for pedestrians but for drivers as well. When any pedestrian is crossing the street, how driver react to certain situation is annotated along with the scene context. Information about scene, like if scene contain any crosswalk, traffic light, or stop signs, are crucial to understand behavior of pedestrians, which very well annotated in this dataset. Most of high-level actions of human can be extracted from their skeleton or bone joints. In computer vision, this task of identifying bone joints or important key points of object is called pose estimation. Detecting the pedestrian and getting the pose should be real time so that our autonomous car can respond quickly. There are two ways to do the pose estimation. First is bottom-up approach, where we detect all the parts of person, then associate part which belongs to individual. Second is top-down approach, where we detect first all the person in the scene, and then we loop through all the people and then find individual body parts within the scene. Both approach have some pros and cons. Top-down approach takes more time since it detects all the person in the scene first, and then loop through each person for the pose estimation. In our study, we have found that a bottom-up approach is better than a top-down approach. If there are more number of people in the scene, it does good job in terms of performance, in terms of efficiency. That is reason why we went ahead with bottom-up approach and finalize to use OpenPIPFAB as pose estimation network. Here we have trained OpenPIPFAB network on COCO dataset and fine-tuned on pose track to extract 2D pose or key point and as well as bounding box information of pedestrians in the scene. There are total 17 key points belongs to the person. So for each person, we get 17 key points, and that 17 key points are represented by three values, which are X, Y, and visibility. Where XY are the pixel locations of the pedestrian in the scene, in the image, and Y is a visibility score of how much that key pose is visible, which ranges from 0 to 1, where 1 is fully visible and 0 is where the key pose or the bone joint of the pedestrian is not visible. As mentioned, JAAD dataset provide scene information like if scene have traffic lights, traffic signs, etc. We can achieve this task either by running an object detection task to know if the scene have this object or not. But if we have additional information like lane marking, crosswalks, sidewalks, etc., then it improves our understanding of environment by various factors. Knowing location of this curb and sidewalk are very difficult to achieve through object detection task. For this, we need semantic segmentation, which associate each pixel with the class in the image space. There are multiple semantic segmentation models, but we decided to go with unit architecture since it is faster compared to other latest architectures and it very well adapt to driving scenarios. It named unit because it has a U-shaped architecture when you look at its layout. Um, the first half of unit architecture is encoder part, where it takes the original image as an input and process it to extract important features and patterns. And the second half of unit architecture is it's a decoder, where it takes the original image as an input and process it to where it takes the learned features from the encoder and creates a map that outlines the different objects in the scene or in the image. So in our perception backbone, we have included semantic segmentation with VGG encoder and unit decoder that is pre-trained on Cityscape dataset, and we have fine-tuned it for JED dataset. In our model, we focus on five things. First is gait, if person is walking or standing. Second, attention, if person is directly looking at the vehicle or not. Third, orientation, the pose orientation of the person with respect to viewing angle. Fourth, distraction, if person is distracted with the phone or not. And fifth one, crossing intent. Crossing intent tells if the person is going to cross the street in next time horizon of next 30 frames or not. Uh, for the first benchmark, we train our model on individual class labels so that we can compare it with further in next architecture. And we have some baseline to compare. For attention and orientation model, we have used joints from upper body. For distraction model, we have used angle between hand and arm joints, as the distraction tells if a person is using the phone or not. An important uh, key feature of the person, if he is using the phone or not, are the hand joints. So that's the reason why we are focusing on certain part of a body for individual task. For attention, it's more like if you are looking at the car or not. So we give more attention on the upper body or the facial structure to see if person is looking at the car or not. Similarly, for gait model, we have used body joints below body joints to know walking and standing, since person can be identified by the skeleton of the walking, or skeleton of the legs to know if it is walking or standing. Once we predict individual behavior, we combine the result of all these models, feed it into SVM, and predict if pedestrian is going to cross or not. Now we have a baseline model which we trained for individual modules. Now we have a multitask learning model where instead of predicting individual modules and combining them later, we train them together to achieve better performance. We have used a sequence of we have tried multiple sequence length where we see sequence length of 30 frames are good enough for predicting to understand past trajectories as well as past actions, and predict what pedestrian is going to do in next 30 frames. Input to multitask learning model are 2D pose and bounding box sequences and semantic segmentation. We got 2D pose and bounding box from OpenPIPF and semantic segmentation from unit. To have consistency in the detection and have the history of individuals detected pedestrians, we have used deep sort, which uses visual features and Karman filter to track pedestrians. In our study, we use 60-20-20 splits for training, testing, and validation sequences. Using object context and scene context, our model classifies gait, attention, orientation, crossing intent, and trajectory of pedestrians. For trajectory prediction, we have tried a few models where one of good models were either a constant velocity model or using polynomial models. Constant velocity models are really good most of the time because car moves constantly in one speed and one direction, and similarly pedestrians are always walk in constant directions. But this model doesn't very well classify pedestrians who are jaywalking, and that's the reason why we wanted to have a better trajectory prediction model, which can understands the scene context as well as predict the trajectory of pedestrian much better than the constant velocity. In our trajectory model, we used LSTM encoded decoder architecture with mean square error as a loss function. And input to this model is 30 frame, and we predict a future 30 frame trajectory of pedestrians. Here we have comparison of modular approach on extracted human joints versus image-based approach, where modular approach is doing better. As seen here, we have tried gait and awareness accuracy on AlexNet, where it's 78%. But once we extracted the pose, and then later if we use this pose as an input to a modular model, then it does a good job in predicting the gait accuracy as 91%, awareness accuracy 87%. So modular approach with the context is better than just running a simple image model. But if you compare the crossing accuracy, multitask model does a better job than combining the individual model and adding the context to them. And that is a reason why we wanted to compare the modular versus multitask models to understand how much difference in the terms of accuracy we will have if we use a different models. We have shown this proof of concept demo in CES 2020, where we have a UI, and using 360 surround view cameras, we have 4 cameras, front fisheye cameras, right and left cameras, and rear camera, and we detect entire 360. We do the perception on entire 360, where we detect a pedestrian in the scene, and in the middle you can also see a 3D view of our LiDAR. I will play this demo video. So here you see the 3D scan, and we understand where the pedestrian is standing and what are their behavior of the pedestrian. As seen here, the pedestrian is going to cross, and we have 4 icons for each of them, where the first icon tells if pedestrian walking, running, or it's just standing. The second icon tells how much pedestrian is aware of surrounding, if he knows the car, if he sees the car or not. We have 3 states for awareness: fully aware, partial aware, and not aware. Third icon is the crossing intent of pedestrian, if he is crossing the street or not. Uh, the fourth is if the pedestrian is distracted, if a pedestrian is using phone or not. And the progress bar below is the risk bar, which tells how much this pedestrian is risky for in the path of autonomous drive. Along with this all information, we also show the scene understanding. If you look carefully, we have a scene where we understand the road markings. We understand where in the scene the pedestrian is standing, and that helps us to understand the behavior of a pedestrian. I will play video once again to see the intentions of pedestrian and how the model is. Now let's talk about the pantomime. Automated driving system need to recognize not only fixed signals such as traffic sign, traffic lights, but also gestures used by traffic police or other traffic authorities. Traffic police command recognition is necessary for special situations such as traffic light failure, accident-prone areas, bad weathers, traffic jam, and controlled traffic by the traffic police. Therefore, autonomous vehicle must be able to quickly and accurately recognize the traffic signals from this traffic authorities so that they can respond in this emergency situation quickly. Most of ADAS system detection already detect pedestrians. So categorizing them further to know construction worker and police can be very easy task given the right data set. On the road, these are not only two categories of people which automated vehicle need to interact with. It also need to interact with pedestrians and cyclists. Pedestrians give important information like waving hand or nodding head when they are crossing the street. Cyclists also gives their intention by hand signals if they are turning right, left, or stopping. These signals should be understood by automated vehicle for safety and comfortable driving behavior. So, in conclusion, we need to detect all the classes of pedestrians and their actions, and that's what pantomime does. The meaning of pantomime is understanding the hand actions without talking any words, and that's what the car need to understand. As all the deep learning as what AI need is a data set to correctly do the right amount of job. So for this task also we need a correct data set, uh, and in order to find the data set for traffic police hand signals, we found this Chinese traffic police gesture data set. This Chinese traffic police gesture dataset consists of 8 types of gestures: stop, straight, turn left, turn right, left turn right, change lane, slow down, and pull over. This gesture dataset provides 20 videos without skeleton data, but it provides ground truth gesture labels for each of video frame. Author of this dataset also have released a paper where they have tried a skeleton-based action recognition method, where they have explored graph convolution-based network as well as the other methods as well. A study in this research paper have contributed two methods: GSE, graph skeleton extractor, and MDGCN, multi-channel directed graph convolution network. The gesture skeleton extractor part is proposed to extract skeleton coordinates information and remove redundant skeleton joints, which improves the skeleton data representation to strengthen the attention in the network. MDGSN is proposed to extract body topological and spatio-temporal action from the skeleton coordinates, which makes better representation of gesture feature and make features interpretable. Since data in previous slide was from different country, we wanted to look for a data set which can be used in USA. There is no data set there is no data set which we can use in USA, and that's reason why we decided to create 5 gestures, out of which 3 were static: stop, turn right, turn left, and 2 were dynamics: pull over and move forward. One of the reasons for creating our own data set was to use gestures which can be shared between uh, traffic police as well as the construction worker. Once we finalized what gestures we wanted for traffic police and construction worker, we wanted to create gestures which are generally used by cyclists as well. We found CASR dataset, cyclist arm signal recognition dataset. This dataset contains 4 arm signals by cyclists, which are stop, turn right, turn left, and alternate right. If you look carefully, these are same hand signals which are used by car drivers when their turn indicators are malfunctioning. Uh, so having such system can be very useful for extending use case to understand hand signals of car driver as well. Since dataset for police officer is very limited due to data privacy, we couldn't find enough images using which we can train our image classifier. Hence, we collected our own data set, which includes construction worker, police officer, and cyclist. Um, in our data collection, we also made sure data represent a busy street scenario where police officer directing traffic and pedestrians are crossing at busy crosswalk. We we collected data at different daytime along with multiple people wearing different props to make sure we have enough data distribution. We have enough distributions in the data. After the annotation and removal of bad examples from data, we got almost 4,000 examples of construction worker and cyclist, 2.5 thousand images for police officer, and 6,000 examples of pedestrians. For gestures, we got data almost 100 sequences for each gestures, where one sequence contains uh, 30 to 60 seconds of frames of person doing gestures, and 500 unknown sequences where these sequences include random hand movements or the transition between one action to another action. We followed almost a similar architecture as we've done for MovePredict. Here, instead of multitask network, we have developed skeleton-based action recognition model, which identifies gestures of road users. For Pantomime, instead of using all 4 cameras of car, we have used only front camera. Unlike MovePredict, here we don't need 360 detection. Police officer and other important actors are going to be appear in front of a car. So we don't need 4 cameras. One front long range camera is enough. In Pantomime pipeline, we detect all the interested object first, that is pedestrian, police officer, construction worker, and cyclist. Since we need a history of each actors to understand their actions, we need to track the pose. For that purpose, we used deep sort here as well. After detection, we branch out processing, where the first branch we classify authorized user, that is ATC classification. and a second branch where we run pose estimation followed by action recognition. Uh, we get all the actions from the skeleton recognition, and the ADC classification tells us what is the category of this authorized user. Uh, we kept this branch two branches separate so that if we don't need to understand the authorized classification, we can discard that branch and we can focus only on the actions of actions which can tell the actions of all the road users, and we don't need to classify them. Since we need to follow certain classifications, we use YOLO V7 detection. For bounding box object detection, there are various methods from faster RCNN to YOLO V7, YOLO V8. Now there are like latest transformer-based detection as well. The reason of selecting YOLO V7 for this task was that it is accurate enough for the task, and it is real time. And we want to, since our pipeline have multiple models, we want a model which is faster enough and doesn't create a latency issue for us. For ATC classification, ATC classification is similar to image classification problem, where we give the bounding box of the detected person and we tell the model, we ask the model if it is a regular pedestrian or police officer, construction worker, or cyclist. There has been a lot of research has been done from past 10 years for image classification, from LXNet to VGG16 to VIP transformer. The reason of using connext here, the transformer-based classification, was since we want to focus on very detailed clothing to know if this is a really a police officer or just a person wearing a blue shirt. We need to understand the features of the person and find a fine tune of features like hat, tie, or glasses if person is wearing or not. So this kind of features extraction was difficult in regular image classification models. Convenext was doing pretty job to understand these features of ATC classifications. Now, for our skeleton-based gesture recognition, we used co-occurrence feature learning from skeleton data action recognition. This model uses a convolution neural network, but instead of using a color channel, we stack the actions of pedestrian of each frame stack together as a channel and give it to the regular convolution neural network, and this gives a really good action category, which tells what is the action of pedestrians. Um, in our study, we also noticed that giving immediate frame is not improving the accuracy, since if we divide our frame into 30, if we divide a 1 second of data into 30 frames, the alternate frames doesn't have much information. So in our training, we skipped 2 frames to have a less number of trained model, to have less number of parameters for the training. And we trained for 2000 epochs. We achieved accuracy of almost 96% when we train our model. We used also the upper body only, since all of this actions uses upper body of the person. We have reduced amount of number of parameters in the model by not giving lower body parts. For setup, we used only one camera, one Valeo camera, which is even 1 megapixel. And since our pipeline have multiple stages of model, we do the detection in 7 millisecond, tracking 2 millisecond. pose estimation 60 millisecond, VRU classification 35, and action classification in 7 milliseconds. This frequency is where there are almost 10 people are included in the scene, and most of them are doing any sum of actions. For road user classification, we got 95% accuracy, and for action classification, we got 96% accuracy. Before moving to the demo, let's discuss about the challenges for the system. Every country have different costumes for police officer and traffic police. As seen here, China and Japan have bluish costume, where in India it's a khaki color, and in France it's white. Even in USA, you can find variety in police costume at different shade, as shown here. California has a dark blue costume and Nevada has grayish looking costume. It is very difficult to generalize one model for all type of police. Along with the different costumes, they also have a different gestures for traffic control. If we combine actions of different countries, they may conflict with one another. So we decided to keep them separate, country specific. Similarly, for the construction worker, there are various color of vest. This can be possible. This can be possible to generalize, unlike police, but having to do so may degrade the performance of system. A few months back, we showed demo in Japan where authorized person who navigates the traffic wears a white reflective vest. It was very easy to adopt new vest for the purpose of demo, as the model was learned to understand the reflective features of the vest. We can also make use of different color of vest to know a superiority of person at the construction site if it was trained only specific to the vest colors. Another challenge if dancer is hired as a traffic police. As a human driver, for us itself, it's confusing to understand what kind of action here police officer is doing. We have showed our technology demo in CES this year 2023, where we have showed the working of pantomime in front of lots of media and all the attendees of CES. I will play the video here. Here we detect four classes where it's where each class represents where each icon represents what class of action, what class of user it is, and we also understand their actions. We just seen cyclist. Now we are seeing the police officer, where police officer right now is telling us to turn left, turn right. Police officer can also say pull over. Here we have detected the construction worker and we are understanding what actions the construction worker is telling us to do. Since actions are shared between police officer, are similar between police officer and construction worker, they can use the same actions but have a different meaning as well. Thank you.
Good. Thank you very much, Jagdish. So I think we've reached the end of our presentation. In case there are any questions, it is your chance to put them into the chat that we can address them. A lot of the work we do here is about trying out new things that haven't been done before. So we find one of the interesting areas for us to work in is really this perception. How can we improve it for vehicles? How can they understand the world the way humans understand the world? There's a lot more detail, a lot more nuance to the way humans drive. And this is something we think that machines will need to be taught with time. And so this is really one of our main study areas here, is to delve into this and figure out how can we see things, understand things in the context of what the state of the art out there is right now. And if there are no questions, then at this point, I would thank all of the participants for joining us today, and a special thank you to the SAE Detroit section staff, as well as Valeo staff, for their involvement in putting together today's presentation. If there are any questions or inquiries about this presentation, please email SAE Detroit section staff at the email address shown here, events@sae-detroit.org, as shown on the screen. And if you're watching this on YouTube, please consider liking this video, sharing it with someone who might find it useful, and subscribing to the SAE Detroit section YouTube channel. Have a great day, everyone.